Okay. Thank you, Stephen, and thank you, Matt, and thank you, everyone, for giving me the opportunity for presenting today. Can everyone see my screen? All good? Okay, fantastic. So tonight I will be presenting on the Jigsaw multilingual toxic comment classification competition that was hosted on Kaggle a few months ago. But just a little bit about myself first. So I'm currently employed at Stem Cell Technologies in Vancouver. And Stem Cell Technologies is a biotech that makes products for cancer and stem cell research. My current job title is a bit of a mouthful, scientific communications operations specialist. Basically, that means that I've been there so long that they needed to give me a new title, but couldn't think of anything better. And so I'm now the operations specialist, basically, because I know how to do most things. My background is in microbiology and biochemistry from the University of Western Australia. That was a very, very long time ago. And I have no real formal background in mathematics, computer science, or data science. So I want to sort of stress that I'm very much a beginner in this. What Matt was just saying about forcing yourself to learn, this is basically the reason I did this. And I've learned a lot. But going back to my job a little bit, what I do is I mostly choose or classify scientific journal articles to be put into newsletters, and also do a lot of tweet writing. So my job is very manual, very laborious, and very repetitive. And because of that, I decided to teach myself some basic Python to help automate some of the tasks. And at this point, I have to give a shout out to Matt Emery, who I'm sure a lot of you will know. I don't think he's here today. I used to work with Matt, and Matt actually developed some quite substantial programs to automate our processes. I'm not quite as good as him, but I've tried to follow in his footsteps a little bit. I am really interested in data science. I am quite new to it, as I said. And again, as Matt mentioned before, I really encourage everyone to ask questions during the talk. And not only that, also please provide insight. There is a portion of this presentation that I'm not that confident on my knowledge of. So if anyone has some extra further insight that they would like to add, please jump in. So just a quick
summary. Thank you so much for your introduction. I just realized we did miss somebody.
Sure.
I think we did miss Nicole with her introduction. Nicole, if you don't mind.
Sorry, no, I didn't. Yeah, I hope I'm not disrupting presentation. Yeah, sorry about this. My apology actually, but thank you very much for finding out that I was missing. So just about myself, my name is Nicole, and then I have been coming from time to time to data science meeting. And I'm currently studying in a master program in management analytics for data science at Queen's University. And I'm currently involved in a project on developing machine learning models for credit risk-related games, which can be adopted in hackathon for data scientists or any of the local workplace. And I just wanted to ask if anyone knows what's going on in the credit risk at commercial bank or financial service industry, and also knowledgeable in machine learning area. I would love to connect with you. Just feel free to reach me out in this regard. Thank you very much.
Thanks, Nicole. I'm sorry, Mark, for the interruption.
No, not at all. Thank you, Nicole. And thanks, Stephen, for picking that up. That's great. So just a bit about the talk I'm going to do tonight. First of all, I will discuss the competition and why it's a really important competition. I will then do some of the exploratory data analysis that I've performed on the data. And then I'll go through some basic natural language processing techniques that I learnt in the process of making this talk. Basically, the way that I'm presenting this entire presentation is kind of like a learning journey that I went through, and all of the different things that I've picked up on. After that, I'm going to attempt to go through some of the more recent natural language processing techniques from neural nets up into BERT, which stands for Bi-directional Encoder Representations from Transformers. I'm going to do this at a very high level, and one might question the wisdom of a beginner attempting to do such a thing, but why not? And finally, I'm going to go through some of the winners' strategies and what they did. So just before I get into the current challenge, I just need to explain that this was actually the third in a series of challenges, and the data came from Jigsaw Conversation AI. And the first of these was back in 2018, and it was looking at toxic comments, toxic online comments, and how to detect those. I will go into what defines toxicity in a moment. But basically what this challenge was trying to do was trying to pick up when someone was writing something, bad and toxic in an online forum. And it was quite effective. It was a good challenge. One of the things that came out of it, though, was that it was incorrectly categorizing certain words as being toxic. For example, the word gay. A sentence such as "I am a gay woman," for example, would have been incorrectly classified as a toxic comment based on the models that people built for this challenge. And the reason for that was because the word gay was almost exclusively used in a negative sense in the training data. So a subsequent challenge in 2019, the unintended bias in toxicity classification challenge, attempted to address this. So basically the challenge here was to build models which could take into account that there's going to be bias in inherent bias in the training data that needed to be resolved. So as I mentioned, this competition is looking at toxicity in online comments, and toxicity was defined as anything rude, disrespectful, or otherwise likely to make someone leave a discussion. Now, some comments when you're online, you might be able to laugh them off and say they're nothing. But of course, we all know that attacks against identity and cyberbullying are really big problems, and they need to be addressed. So this is a really important problem to solve. This was a code competition, which meant that submissions had to be made by an output from a notebook or a script that was directly put into Kaggle. This is in contrast to, I think, most of the competitions where you simply submit a CSV with some predictions based on a model that you've made, and that's what gets tested against. This one, you actually weren't allowed to use anything except running the code through Kaggle. There's a good reason for that. There's a sort of a benefit for this, and that means that everyone in the competition is basically using the same hardware. So that kind of levels the playing field, because obviously people who have done a lot of Kaggle competitions will probably know that if you've got a super powerful computer, you can run a lot of really big models like fast and make a lot of submissions. So that was interesting. And the comments themselves were from Wikipedia talk pages or civil comments. I'll go into what Wikipedia talk pages are in a moment, but Civil Comments was a company that created a very user-friendly platform for detecting toxic comments. It was like a plugin you would put on your browser, and it would, I'm not actually quite sure how it worked, but it would pick up this saying that this is toxic. But this is where the data for training and for testing came from.
Hey, Mark, quick question.
Yep.
For running the requirement of running the code in a notebook, did that include training the model as well?
Actually, no. You were allowed to train your model wherever you wanted. Okay. So saying that it was leveling the playing field is not quite right. You could train the model wherever you wanted, but when you ran the actual like code to test the predictions, whatnot, you would have to run it through Kaggle.
Okay. Yeah. Leveling the playing field a little bit, I guess.
A little bit. This is an example of the Wikipedia talk comments, and I didn't even know Wikipedia had this. Every single page on Wikipedia has a section where people who edit the pages can discuss their ideas, and this is kind of close to home for me, being Australian. This is a small section of the Australian talk page discussing the number of reptiles in Australia. Who knows, this would have been a contentious issue, but here it is. And what you can see is there is a series of comments. Can everyone see my mouse moving around on the screen? Yep, okay. And where you can see an indentation, this is where someone has replied to a comment. And what you've got here is, you can see that they've got a username and there's a timestamp. And this is all very, this, if you do read this, you can see it's quite a civil discussion. There's no animosity in here. But as you can imagine, being an online thing, when people get their pride involved and people telling others that they're wrong, there's inevitably going to be some toxicity in the way that people deal with each other. So this competition, you were encouraged to use a model called Multilingual BERT. And again, BERT stands for Bi-directional Encoder Representations from Transformers, for zero-shot learning. Okay, so there's a few things here. So BERT was a deep learning model that was made by Google back in 2018. And it was trained on, it's basically like a great big pre-trained model that they trained on with Wikipedia and some open source books. And the idea behind it was to basically have this gigantic model that you could use to do all sorts of natural language processing applications, including something called transfer learning. And what transfer learning is being able to use a model which has been developed with one set of data and then use it on perhaps a completely different set of data for a different purpose and have the model actually do what it's supposed to do. And this is also kind of what zero-shot learning is. It means that you're not having to rely on any training data. So you could basically just use this pre-trained thing and it all goes well. However, you could use whatever model or training data that you wished. You would normally need to make these publicly available on Kaggle, which means that everyone else in the competition has access to it and can use it as well. And the suggested BERT model that they were talking about. Oh, sorry, I just need to go back to mention that what I was discussing, that what Google made in 2018 was the BERT model. There was a second version that they made a few months later called Multilingual BERT, where they did basically the same thing, but they used a multilingual corpus, so lots of different languages to pre-train a big model, but basically for the same purpose. So this model, you were able to fine-tune it with English data, so an English training set. And then the idea was that you were going to predict toxicity in non-English data. So that was the actual, that was the idea behind this competition. You have a model mostly trained with English to detect toxicity in non-English data. So why is this competition really important? And obviously, being able to detect and deal with toxic comments online is really important for the reasons that I mentioned before, but also is really, really interesting and really cool to demonstrate the potential for such a pre-trained multilingual model for transfer learning. You just make some massive model and then just use it for everything, or lots of different things. I mean, you can imagine the sort of application where you might have a language which doesn't have a lot of linguistic resources to make its own model. So, for example, some sort of indigenous language, and if you're able to build a natural language processing model from English and Spanish and Chinese and other languages that have a lot of linguistic data, and then successfully use that for a language doesn't have a lot of linguistic data, that's really cool. That'd be a really good outcome. So I set myself the goal of understanding the data in this competition, and also how such a model would work. Okay, so just a little thing about, this is kind of an aside. When you do a Kaggle competition, you're relying on usually two things: a CPU, like on your computer, or like a graphics card, like a GPU, to do the training. In this competition, you were given the option to use a third piece of hardware called a tensor processing unit. And the competition encouraged the use of these. Essentially, without going into a lot of detail, these are just like a specialized piece of hardware that is really good for deep learning tasks. And Kaggle actually gives you a period, like an amount of time every week free to use these. It gives you 30 hours a week free. So they basically encourage you to use these. Some competitions don't allow you to do notebook submissions on tensor processing units, but you still are allowed to train a model with them. I'm not going to go into too much detail with this, just because it's sort of an aside, but I thought that was an interesting point to bring up. Oh, another thing is I actually tried running some code just on like the normal like a CPU, and then I did the same code on a TPU, and it was like 100 times faster. It was amazing. So, oh, and the other thing is that Kaggle does actually provide some boilerplate code. If anyone's interested in trying this out, like that can actually, you can just pop into a script which will get these things up and running. Okay, the evaluation metric for this competition was the area under the curve for the receiver operating characteristic. So the way to describe how this works is, if you imagine you're doing some sort of classification problem, and you've set yourself, all the values that are coming out are in between 0 and 1, and you're saying that the threshold is 0.5, and anything above 0.5 is classified as positive, anything below 0.5 is classified as negative. What would happen is that you would be able to plot your outcome on a confusion matrix, saying that you'd have a bunch of true positives, a bunch of true negatives, false positives, and false negatives. And from that, you would be able to work out the rate of the true positive rate and the false positive rate. But just say you wanted to, for a particular classification problem, you wanted to change that sort of threshold. So for example, some sort of disease diagnosis. Now, if you're diagnosing a disease, you'd want to probably be erring on the side of caution when you're giving a classification. So maybe instead of having a threshold of 0.5, you would reduce it to 0.3, for example, and anything above 0.3 would be positive and anything below 0.3 would be negative. And that may mean that you would pick up more false positives, but because you're diagnosing a disease, that's potentially a good thing, because you'd rather tell someone that they have it when they don't, rather than they don't have it when they do. In modifying the threshold, of course, what's going to happen is that the number of true positives and true negatives and whatnot is going to change, which in turn modifies your true positive rate and your false positive rate as well. So if you were to graph the various false positive rates and true positive rates on a graph here, what you would end up with, if you were to modify this threshold, you would see that the number of true positives would maybe increase depending on the threshold getting to like a better point. Like if the threshold should be around 0.6, for example, and you were trying a bunch of thresholds, you would see like a sort of a maxima occurring where you would have the greatest area under the graph at a certain point. I'm not sure if I'm explaining this very well. Math is not my strong point. Does anyone have any sort of insights on this? No. Okay, so hopefully I explained that fairly well. But anyway, that's the evaluation metric for this competition. Okay, so the data that was provided was, we had a set of training data from the first competition from 2018, and these were English comments from the Wikipedia's talk page. There was training data from the second competition in 2019, and this was a data set from the Civil Comments company, and these had a range of additional labels. The additional labels were, because this was looking at bias towards perhaps like minorities and different identities, there was identities like trans and homosexual, and also like different kinds of races and stuff like that, that people were labeled. We then had a set of validation data. These were all in non-English languages, and the validation data, of course, is to fine-tune your model. And then the test data is comments from the Wikipedia talk pages in non-English languages also. Another thing that they did was they also pre-processed all of the data sets, every single one, specifically for BERT. So you didn't have to do that if you didn't want to. You could actually have some stuff that you could just throw straight into the model right from the very beginning. So this is the beginning of my exploratory data analysis. What I've done here, I've just got some examples of the comments in the training data. And I've got two groups of 5. The ones on the top are the clean ones, the ones that don't have any tags related to toxicity. And the ones on the bottom are the ones that were tagged with some kind of toxicity. You can see that I've had to cover up some of the words there because they definitely were too offensive to have in a public presentation. All of these tags were crowdsourced. So the way that they were tagged is that this was a public thing where people could go on and they would say, okay, yeah, this is obscene, and someone would just go through and check everything themselves. This, I think, may have introduced perhaps some inherent bias in the data. I just know that obviously if you got a bunch of different people doing tagging, people are going to be possibly tagging things in a slightly different way from each other, which may introduce some inherent bias. I did think of something else as well in that perhaps, because this is talking about toxic language, I'm going to assume with absolutely no evidence to suggest this, that a lot of people doing the tagging are probably going to be white, straight, cis, and probably male. And I would basically, this is a vast generalization, is that that sort of demographic may not be sensitive to something which is toxic to, say, someone like a trans person. So they may not have picked up on some of the toxicity of some of these comments. So there may be some inherent bias here. But what you can see is there, so obviously the clean ones don't have any tags, and there were 6 that they could have. There was toxic, severe toxic, obscene, threat, insult, and identity hate. And from the ones that were considered toxic, they were able to have multiple tags depending on what they thought was going on there.
Sorry, Mark. What is?
Yep.
Go for it, Stephen.
What is the difference between severely toxic and toxic? Is there a guideline on the separators?
That one, there was no actual hard and fast rules for that. I found the instructions for people tagging, and all it basically said was toxic is like a comment which would force someone to leave a conversation. Severely toxic is a really bad a comment that would force someone to leave a conversation. So it was definitely up to people's interpretation. I'm not sure if does that answer the question? Yeah. Good. I actually thought someone was going to ask that, so I specifically went and found that out.
Yeah, it just highlights the point that you just brought up of how these classes are not super well defined, and there might be some exact same segments of text that one person would label as a 1 and another person would label as a 0. So it's tough problem to overcome. I wanted you to go back one more slide. I'm just trying to understand all of this. So the training data comes from the 2 different competitions that they had hosted earlier. And then when you say validation data and test data, can we go over those one more time?
Well, I've got a few slides on those coming up soon, so I don't know.
Yeah, we can wait
for that.
Yeah, let's wait.
Hopefully my slides will explain what's going on there. There were a lot of files associated with this competition. So I had a look at the number of missing data, and I did like an info method here to have a look at what was going on. And if I have interpreted this correctly, if you've got the index equal to the number of objects in each of the different columns, you can assume that there's no missing data. Am I correct in that assumption? So by saying that there's 223,549 entries and every one of these has the same number of objects, I'm just assuming that there's no missing data there. I'm guessing that's the best way to do it. And the first thing I looked at was the length of basically the number of characters in each comment. And you can see here the green is the clean ones, and the blue is the ones that I've called dirty, the ones that have got some sort of toxicity related to them. And it all kind of makes sense here. It's very positively skewed. I did notice though that perhaps the more toxic ones are slightly more positively skewed, which would say to me that a shorter comment may indicate more toxicity, which kind of makes sense if someone's just telling someone to F off. That would kind of follow. So in the training data, I looked at the number of tags and how many tags were associated with each. Sorry, the number of tags for each comment, and you can see that the classes here are very, very unbalanced. The majority of the comments were actually clean. Of the 220-odd thousand, 201,000 of them had no tags whatsoever. And then of the toxic tags, they were also quite unbalanced. You can see here only 689 were considered a threat. So this, I think, would affect some sort of, if you're building a model with this data without any modifications, I think it would affect the outcome of that model from the way that I interpret this.
Hey, Mark,
Yes.
did you find any of the clean ones to be unclean, or like, because you said there is bias, is there, can that be a chance that that's happening too, the other way?
Yeah, for sure. So you're saying that one of the clean comments is actually toxic and someone just hasn't tagged it properly? Yeah, no, totally. I think that would definitely be a possibility. I didn't actually look at that. I didn't sort of scour through the clean comments and try and find something which was misclassified. That would have been a good idea, though.
Sure.
Yeah.
Mark.
Yes.
So is it true that the toxic is always true for a toxic comment, and then one of the other ones can also be true, or is that not how it works?
Absolutely. So you're saying that with multiple, they can have multiple tags.
Yeah, but then is the toxic always true if they have another tag?
I beg your pardon. No, that's not actually the case. So it could be obscene but not toxic, or an insult and not toxic. Yeah. So with the exception that severely toxic will always be tagged also with toxic.
Okay.
Yeah, no, good question. Yeah. So no, they don't. It's not linked in any way. So what I wanted to look at here was the number of multiple tags per comment, because I noticed that obviously in that slide a few slides ago, you could see some of them had a lot of multiple tags. And looking at this graph here, you can see that 0 tags had 201,000, which makes perfect sense because that's the same number of clean tags we saw here. And there was quite a few that did have multiple tags. So what I wanted to look at was some sort of correlation between and this actually kind of goes back to what you just mentioned, Anu, the correlation between whether something was tagged as toxic and if it was tagged as one of the other tags as well. So I've done like a cross-tab correlation here. It's a bit confusing, but each of these here is like a block of 4, kind of like a confusion matrix. But you can see this first one is saying there was 202,165 that were not tagged with either severe toxic or toxic. 19,400 that were classified with toxic but not severe toxic, 0 that were classified with toxic with severe toxic but not toxic, and then 1,962 where they were tagged as both. And you can, if you look at the others, this actually just going back to again what we were just talking about before, there were no instances where something was tagged as severe toxic but not toxic. So it was always if something was classified as severe toxic, it was always classified as toxic as well. And if you look at the other 4, you can see if something was classified as only obscene but not toxic, there was 588. But both obscene and toxic was 11,500. And it's kind of the same with the rest. There's a small number that were classified with just the non-toxic tag. But usually when they were classified with one of these, it was also classified as toxic. There was a strong correlation.
So this seems, there must be some very subtle art to constructing a comment that ticks one of these boxes, but doesn't tick the toxic box. I mean, the sum across the top row there is I don't know, 1,000-ish out of what, 200,000. So it's like 0.5%. But do you have any, is that just flaws in the data, or do you think there is actually such a thing as these comments?
I think so. I know, did I have a threat in here? No, I didn't. That's a shame. I did have a look at a couple, and some of them were actually pretty threatening, but not. I don't know. It's very much open to interpretation. That one of them that I saw said something like, "If you don't make these changes, I'm going to report you to the moderator." So it's kind of like not that he's not taking it personally, but that is a threat, really, when you think about it.
Yeah. Okay. Yeah. If you keep making toxic comments, I'm gonna get you banned.
Right. Exactly. Yeah. So I know what you mean. It's pretty much any of these things really should have been considered toxic as well. But yeah.
Yeah, especially identity hate. How can it be identity hate but also not toxic?
Right. I guess it does go back to the whole inherent bias thing, and someone's not really picking up on something. So yeah. Does anyone else have any questions on this?
Yeah, are all these equally weighted when your model is understanding that something is toxic? Like, so if it's just identity hit, or if it has multiple tags, does it, the weight adds up or something, or like?
I don't know. I'm not sure how that would work.
Sorry, maybe I just maybe
No,
this
it's a good question.
is not okay.
Does anyone else have any idea about that? If it's like something that's really unbalanced like this with the classes.
Well, actually, maybe a simpler question. The target for the competition is all of these tags, or is it just the toxic tag?
Oh, right. No, it's only toxic. So with the target for this, it's either a 0 or a 1 to whether it's toxic or not. And I'll come to that when I get to the testing data. So yeah, that's right. Good point. So there isn't any of this granularity in the output for this model. It's just either a 0 or a 1. Yeah.
But I think the question could be interpreted more generally about just the imbalance of the classes and how that affects the model. Is that right, or?
I just wanted to understand the relationship, if there's these things add any value to the prediction you're making, or is it like it's just for our understanding or EDA?
I've done this mainly for EDA. I'm afraid that I'm not quite up to the point where I would be able to understand how much of an effect this would have on a model. So I'm hoping that other people might be able to answer those kind of questions.
Yeah. I mean, for one, it's worth reflecting on the fact that like this isn't, I presume this is not information that you have at test time. So like in model development, using these kinds of labels is challenging. Sometimes you might do something that's like multitask. I don't know if any of the solutions later in the presentation do that, but like if you train a model to predict both toxic and severe toxic, maybe it got better at predicting toxic somehow.
I think I saw a few of the examples where they would actually remove all of the classifications except for toxic. They just got rid of all the other 5 and trained on just toxic. So I think maybe they were just trying to simplify it that way. Okay. Another thing I looked at was the proportion of unique words in a particular comment. And this graph shows you like what the percentage of unique words in a comment was. So what that basically means is in a comment where each word is used only once, it would get like 100% because each word it's only unique words. Nothing is being repeated. And if you look at this, you can see that on the right-hand side, the dirty and the clean comments follow a pretty similar sort of trajectory. But over on the left, I'm not sure if you can see that, but the blue line, the clean line, is very close to the x-axis, but there's a little bump in the red line for the toxic ones. And what that says to me is that there's a proportion of comments or toxic comments that basically just had a lot of repetition. So I honestly don't know what that might have been. They're obviously just saying the same word over and again, probably something offensive. So yeah, that was a really interesting little thing that I found. This here over here is just an example that I thought of. I don't really know what what it would have looked like. And then I also saw what I thought might have been a potentially leaky feature. About 5% or just under 5% of the comments in the training data had an IP address in them. And these 2 comments I've included were 2 comments that had the same IP address. So we could probably assume that they're from the same user. Now, if you were to use this, if you were to actually like specifically make a feature out of this, I definitely think that might skew the output of the model and probably make it overfit from what I understand. I don't know what the effect would have if you were just to ignore it, but still left these comments in, even with these IP addresses. I don't know what that would have actually done to a model or not. And I don't know whether or not you should remove these comments first because they might skew it in some way. These are the numbers I was talking about here. So there's a IP address down the bottom of each of the 2 comments.
I think this is the sort of thing that is really good to explore at this stage because it's the sort of thing that might lead the model to overfitting in certain ways that you can try to avoid. So if the deep learning model is actually if the architecture that you have that's set up is actually able to identify that and make that into a feature of its own, it might just learn to pay attention to that one IP address and ignore all the other information in the text that's actually indicating whether it's toxic or not, which would be useful for the model to actually pay attention to, right? So
yeah.
Yeah, that's interesting.
Yeah, thanks. That's I also found that a lot of them had, well, no, there was a bunch of them that also had usernames in them as well. There's this hardcore Metallica fan. So that's is basically the same thing, that it's got identifying information in the comments. Okay, so the validation data. So hopefully this helps with what you were asking about before, Matt. The validation data was a series of comments in different languages. In this case, there was 3. There was Spanish, Italian, and Turkish. And all you basically got was the comment, the language in a 2-letter code, and then a 0 or a 1 to say whether it was toxic or not. And the breakdown of languages, these seem fairly balanced. You've got, this is Turkish, Spanish, and Italian. I don't know, they seem to me like they're fairly balanced. But this graph down at the bottom here shows the clean on the left and the toxic on the right, and they're very unbalanced. There's, again, kind of similar to the training data. There's far fewer toxic comments than there was clean ones. Did that help? Is that what you were looking for before, Matt?
This is useful. I was more just interested like where it was coming from, and was this the data that you were being scored on, I guess? Or you could train on this. This was also training data that you would expect to fine tune to, or? Yeah,
well, I guess, I mean, from what I understand about like the validation is that you would build the model using the English stuff and then fine tune it with this stuff. I'm guessing because the testing set is also in non-English languages that you would probably want to use this. You would want to hold this set of data off while you're training, so you didn't overfit or something like that.
Yeah, you mentioned it was a 0-shot learning competition. So
sorry, I probably didn't explain that. It's not technically 0-shot because you do have training data to fine tune it. The 0-shot was more for BERT itself, like the actual model of BERT is kind of like for a 0-shot learning. But sorry, I should have made that a bit clearer. It's this competition itself. You do have data to fine tune your model.
Okay. So the way I understand it, you've got a few different training sets that you were provided from previous competitions, and then there's another essentially training set that they give you that you've called validation set here that you can further fine tune your model on. And then finally, there's another validation set, there's another testing set which you don't have the answers to that you submit to Kaggle, and then it gives you a score back. Okay,
bingo. That's it. Yep.
Awesome.
And finally, right, the test data. So this was basically the same thing as the validation, except of course you don't have whether it's toxic or not. Something interesting about the test data is that it actually has 6 languages. Excuse me. Turkish, Portuguese, Russian, French, Italian, and Spanish. And the fact that there's 6 in the testing set rather than only the 3 in the validation set, I don't know what that would have done. I don't really know what the effect of that for if you were fine tuning a model with only 3 and then all of a sudden showing it 6 different languages, especially one that's like maybe as different as Russian that it hasn't seen before. I don't know what kind of an effect that might have. So anyway.
So I kind of feel like that is testing the 0-shot learning in that sense. Yeah.
Yeah, that makes sense. Right. That makes sense. Okay, so
and sorry, can I just ask you, BERT? It's the multilingual BERT is trained on, like, of course, multiple languages, but is it trained on like matched text in the sense that like, is there a part of this training where we have like some text in both English and Russian, and then we learn to translate, or are they like fully separate corpuses?
I don't know actually, but what I do know about, I'm not sure if they have like the same text in different languages for training. I do know that the multilingual BERT model though doesn't know what language the input was. Basically they've chucked in, there's like 30 or 40 languages. They just kind of threw it all in. And multilingual BERT, I think, is actually classified as a monolingual model because it treats every one of its like all the tokens that is built from all the different languages as one language. So if you look at all the tokens in it, there's English and Chinese and Swahili and Turkish and everything, but it doesn't know which language something is from. And I don't know if that's kind of related to what you were asking.
Yeah, probably. I mean, I guess like the fact that that we might in this competition somehow like use that validation set to succeed at this test set with languages that are completely absent and so on. Like, yeah, there's something magical about this, right?
Right.
Yeah.
I'm sorry, it's probably just a continuation of that. So does it mean that they have like the same embeddings for each word in each language? So I would assume that it's just getting the embeddings, and it means that it has to be matched one-to-one in each language, right? Which is quite a task, I have to say, because you don't have like a good translation for many, or you have several translations for one word in a different language. So I'm kind of like puzzled on how they did that.
Yeah, I'm not sure.
Okay, thanks.
Does anyone have any insight on that? Okay.
I don't know if it's an insight, but I was just wondering whether it's actually based on the meaning of the words or also on like characteristics of the comments, because you showed quite a difference, for example, in length, or I don't know if you can say anything about that.
You mean the BERT model, how it distinguishes between different characters?
Well, how it deals with different languages, I guess.
I think when it the BERT tokenizer. So when I'm going to get into the pre-processing stuff in a moment, but the way when it tokenizes the words, it does break down words from different languages. And when you look at the actual list of tokens, it's usually just like a part of one word.
Okay.
And it has all of the different scripts and all the different languages all mixed in together. As far as I know, and a very big qualification on the limits of my understanding, because it doesn't know what language one of these tokens is from. It just kind of thinks this is a token that's in my model. It might be from Russian, or it might be from some other script or whatever. But it doesn't actually know what language it is. It just
I just looked into the Wikipedia on the BERT, and they said that it's a plain text kind of conversion embedding. So they take the word. It's even the true for English. So the example there is he's running a company and he's running a marathon. Running would be exactly the same embedding, or like a code for each. I mean, for each sentence, right? So, and I guess that's what they're doing for multilingual as well. They just take the word running, take the translation in a different language, like the most popular translation, let's say, first in the in that vocabulary, and then that's it. That's how they do it.
Right. No, that makes sense.
Which I guess the only way you can do it. Like I cannot imagine any other way how they can do that.
That's cool. Thank you. So after I looked at the EDA, I just wanted to discuss some of the different natural language processing techniques that I've sort of picked up. And of course, when you put in data to a machine learning algorithm, you have to process it in some way. You can't just dump in a bunch of words and hope that it's going to work. So especially for natural language processing, you need to turn the words into some sort of something that it can understand, numbers basically. And the example I've got here is an example of the BERT preprocessor with two of its steps shown, tokenization and then converting tokens to IDs. I'll go into those in a moment, but basically you can see there's a comment on the first two lines. It's then split that into different tokens, like different parts that it can use, and from that it makes it converts those tokens into IDs. I'm not going to explain this too much because I'm going to come back to this. But the first step, tokenization, basically this is where you turn every word or piece of punctuation into a token, like a piece. And what I've done is I've gotten the first comment from the training data and just tokenized that. I can't remember which tokenizer I used. It was one of the ones from Scikit-learn, I think. But basically you've ended up with a bunch of essentially what it's done is broken it up into words. And it does a pretty good job. Some tokens aren't like perfect, like for example, you've got weren't has turned into were and then nt But I guess that kind of makes sense because weren't is a contraction of were not. And it also includes all of the punctuation in there as well. But of course, if you're putting in data into some sort of machine learning algorithm, you want to reduce the amount of input. So one of the things you can do is like get rid of certain words that don't have much meaning. So one of the ways you can do this is to remove something called stop words. So stop words are words that, as I said, don't have a lot of meaning, and these are things like the and is and to, and they generally consist of the types of parts of speech like articles, prepositions, conjunctions, pronouns, those kinds of things. The natural language toolkit, which is a really great natural language processing package for Python, includes 179 English stop words. I've taken that previous set of tokens I made in the last slide and removed all of the stop words from it. So we started off with 49, and I've removed 19 of those to get down to 30 words. So that means that what we're putting in is now most of these words are going to have some sort of valuable meaning. They're going to generally put something good towards the training. What I decided to do at this point was to look at go back to some EDA and just have a look at the data again. What I did is I removed stop words from the comments just to see what the most common words were in the training data. So what I've done here, I've got the top 30 word frequencies after the stop words have been removed. And this is all of the data. This is the clean ones and the toxic ones all mixed in. And you can see the kind of words we've got. You've got things like page and think, Wikipedia, please, edit, may. These are all words that you would associate, with polite, constructive discourse, which is kind of what the point of the Wikipedia talk pages is. But when you look at the toxic data, what the kind of words that you've got here, and I had to remove a bunch because they were like seriously offensive. You've got words like suck and die and hate and stupid, and a lot of these are in capital letters just to emphasize how angry these people apparently were. So you can definitely see a difference in the kinds of words that were in the two sets of data. Going back to NLP techniques, to further reduce the number of words that you're going to be putting in, you can do this process called stemming, and its big brother, lemmatization. So stemming is the process of finding words that have similar meanings and reducing them down to a single token. What I've done here, I've used one of the stemming things from NLTK package, and I've tried to stem studies, studying, cries, and cry. And as you can see, the output isn't really what you would expect. Studies and studying turns into study, but it's spelled wrong, and cries and cry does the same thing. So the stemming process here isn't really that effective, or very accurate. So there's another process called lemmatization.
Well, I don't know if it's fair to call that inaccurate. I mean, maybe that's just the standard protocol is that we map the varieties of study to STUTI. And then as long as we always do that when we train and test our model, then fine. You know what I mean?
Well, that's an interesting point. So even though the word is spelled incorrectly, as long as it has the same kind of general meaning, then it will still work?
I mean, if we're mapping English into a universe where these words all map to studi, we kind of did, as far as the model is concerned, we invented this new word that's standard, and the fact that a human doesn't quite recognize it maybe isn't so important.
Oh, okay. Oh, yeah, that's a good point. I never thought of that. Yeah, that's a good point. But then going on to the lemmatization, which is a slightly more sophisticated version of it, I did the same words using the lemmatizer again from NLTK. And studies turned out to be study. Studying stayed as studying. And cries and cry both came out to be cry. So again, I guess even with both of these, they're not perfect because you would expect studying to be reduced down to study as well. But in this case, it didn't pick it up. And then finally, vectorization. So this is where you want to get your list of tokens into something that is machine readable. And a really common way of doing that is the bag of words approach. And this is basically where you're taking your comments with your tokens from your comments, and you're making sort of like a list and saying that if a word exists, it gets a 1. If the word doesn't exist, it gets a 0. So what I mean by that is I've vectorized these two comments that I had up before, and it's made a single list of all the different features of all the different words and tokens, and then to vectorize it is made two lists where one of these exists in that comment. It gets it basically counts it, so it gets a 1 if there's one of them, it gets a 3 if there's 3, and if one of these words doesn't exist in that comment, it gets a 0. Normally when you do some sort of vectorization, you would have a lot more zeros in your array or in your vectors, because a larger data set is going to have a lot more words. It might have 50,000, 100,000 words. So each vector is going to have 50,000 or 100,000 elements to it. And of course, one comment might only have 30 words in it, which means that there's only going to be 30 of those that actually has a number associated with it. The rest are going to be zeros. And now it's ready to be put into some sort of machine learning algorithm. But wait. So the BERT tokenizer vectors don't look like a bag of words vector. If you look at the way that the BERT tokenizer works, is that it comes out as a list of numbers, but they're not like small numbers like 1s and 2s and 0s. They're much, much larger. And what I also wanted to emphasize with this is that there's different forms of tokenization and preprocessing. BERT uses a different kind of tokenization called Wordpiece tokenization. In that it actually breaks some words up. You can see here Warren has been split into 2, Glenn's has been split into 2. And then when they get their IDs, each one of these numbers is like a unique number that associates with a specific word every time. So we could say that the word pretty would always be associated with the numbers 108361. The BERT model also adds a bunch of other tokens in. The CLS token, which adds to the start of any input sequence, the separator token for when there's like a sentence break, and then a mask token. I can explain how these work a little bit later on when I attempt to explain how BERT works. Any questions about this so far?
I have a question.
Yes.
I just was wondering, was there a reason why the numbers and special characters are left and then not removed during a pre-processing procedure?
Which characters do you mean?
So the numbers and special character, for example, I think the other slide had just numerical values. And then I also see like in the next, like for example, 205 and 27, 38, 50. So those are tokenized words, but then looks like those were not removed during a pre-processing. And also in the next slide, I see some special characters, like not text, but like say, for example, I think just third from the very last tokenized word. So it's like sharp and lens, for example.
Okay. Actually, to go back to this slide, I actually forgot to remove the stop words when I was doing the vectorization at this point. So you can see there's words like it and in and all that in there. I don't know what would remove numbers. I would expect, and someone can contradict me here, I would expect that numbers would not get removed with just your basic NLP pre-processing.
Yeah, there's a lot of different ways of handling it and a lot of different ways of different strategies that people have used. One thing that a lot of people try to do with numbers is just try to normalize them, because if it's a number, it's typically a number and you should treat all numbers the same. So they'll just say, 205, 27, 38, 50, all those can all be replaced with the same tokens, so that the model learns that, hey, this is what a number looks like, and this is what in effect a number has on the meaning of the sentence, as opposed to actually trying to figure out what that number does exactly in its magnitude. So that would be like a normalization technique. You could also just remove them. But yeah, I also had a comment on the next slide.
That's good to know. Thanks, Matt.
One of the things that BERT does really well, or one of the reasons why it's not necessarily just BERT, but it's this Wordpiece tokenizer, is it handles out of vocabulary words, right? So the last one you pointed out was the hashtag lens. But what it's saying is that it never recognized glens as a token that occurred very often in the text. And so there was no way for the model to understand what glens really meant. And so what the Wordpiece tokenizer does is it kind of just searches through all the frequency of like the common characters that happen often next to each other, like by frequency, and it will take the top, however many, 100,000 or 110,000 of those, and then represent those as meaningful tokens, and then it will break the sentence down to only be represented by those. And so if you have an out of vocabulary word, rather than providing the model no information about it, in this case, it provides that there was a G and then there was a hashtag LENs. Now, I actually don't think that's very useful information for the model in this case, but in other cases where there's common like ing endings and common sequences that happen at the start of the words, I'm not good with my vocab, but yeah, it does become a useful technique.
So I had a follow-up question on that, and Matt, you can answer as well. Just I'm not clear, like, so does it not understand named entity recognition, or if we use that, does like Glenn's and Warren, does that become easier to interpret that these are people's name or these are associated with things, and then it doesn't, split it? Is that something that's done normally, or maybe this is just out of context here?
No, it does sound like a plausible technique to try to do some more normalization, to do some named entity recognition and recognize people's names or proper pronouns. And then I guess you could just replace it with that. If that pronoun hasn't happened often enough in the text, rather than just giving it an unknown token, you can give it that at least it's like a name of something. I think that sounds like a reasonable approach. I haven't seen it done, but I haven't been keeping up that much with this field. So
sure, thanks.
Even though I said I was NLP expert, yeah, there's a lot going on in NLP.
Yeah. Sorry.
Sorry, go ahead. I'm sorry.
So the way that it tokenizes, does that mean that different languages get the same token if it's the same word?
I imagine so, or if it's the same sequence of characters, I would imagine that's how it works. I've been, while Mark's been talking, I've been trying to learn about multilingual BERT because I haven't come across it, and I was actually pretty surprised that it's able to take all these different languages as the same input and somehow make it work at the end. But
yeah. I did have a look at. Sorry, Matt. Yeah, I did have a look at the tokens in the various languages, and I think if it came across the same characters within exactly the same script, you would assume it's the same like token. So yeah.
I guess just one last question was I thought that leaving those like numbers or like special characters in, for example, here would reduce the optimization of the machine learning model. So then, but I guess also depends on what kind of features we are looking at when we try to analyze this. So in this case, is it better to actually remove them to optimize a result? What I mean by optimization is like getting a better prediction as to what we are trying to get at here. I'm not sure if it function as noises instead of being useful.
Not sure. It's a good question.
It definitely depends on the task you're trying to solve, right? So I would say cases like punctuation could be meaningful if it's toxic or not. Like I'd imagine there's some toxic comments that use a lot of exclamation marks, or you can imagine somebody like overusing punctuation and it becoming toxic. So I think you would want to keep all that information in if you could, and you might want to split it up into different tokens and split whenever punctuation occurs. In terms of numbers, again, related to the case, related to this task, yeah, that might be something you could ignore. And the more things you can ignore, the better you'll get, because it's essentially just making the job a little bit easier for the model, and it avoids cases where you might be overfitting to like IP addresses or something you don't think should be meaningful. So it's hard to answer that question generally. It always depends on the task you're trying to solve.
Cool. Thanks for everyone for the good questions. Thanks, Matt. That's been really great. How much time do we have left? Is it? We finished at 8, right?
Yep, we're looking at 15 minutes left.
Okay, I might actually skip ahead a couple of slides and just go straight into going through neural nets into BERT. I was just going to talk about before, very quickly, padding. basically the way that when you input sequences into machine learning algorithms that want to be the same length. So padding basically just adds a bunch of tokens to each side, either at the front or at the end of sequences. And then embedding is the way that you get meaning between words. So there's a bunch of different embeddings which have been pre-trained, like Word2Vec and GLOVE, which I'm sure a lot of you might be familiar with, that you can basically use as a sort of a first step. When you put your input through, you can then work out the different meaning, like semantic similarities between words like king and queen both being royal and orange and apple both being fruit, for example. But I'll go through that. Basically, what I wanted to do here is I found a really good notebook by a Kaggle user called Mr. Know Nothing, who has a terrible username because he actually knows a lot. And I basically wanted to go through his notebook and just point out the different things that I learned. And this is the point of the presentation where my knowledge is the spottiest. So if someone wants to add some insight to these things, I'd be very welcome. Starting off with neural nets, though, I'm sure a lot of you know how these work, but basically, neural nets, you have a series of inputs that go through a series of layers with neurons in them to an output, and in between each layer, you've got weights between the different neurons, and each neuron itself has some sort of bias associated with it. So it can the information can flow through in different ways. And during training, if the output isn't quite what it expected, you can then modify those weights and biases in a process called backpropagation, and it does that recursively or repetitively until when it's training, it comes out with the correct outputs. But with a vanilla neural net, at least, the inputs and the outputs are all independent. And that's not necessarily a great thing for natural language processing because words have meaning when you compare them to each other. So, for example, you got this sentence here called, he said Teddy Roosevelt was a great president. I stole this from one of Andrew Ng's presentations. I'm not sure if anyone's seen this. Okay, when you look at this, you know that like Teddy Roosevelt, for example, those two words have some sort of connection because it's a name. Teddy Roosevelt and president has a connection because you might know that Teddy Roosevelt was a president. So doing everything completely independently isn't necessarily a great thing. So enter into the recurrent neural net, and what these do is essentially the same sort of thing. But what you can do here is that you can have a series of basically steps where a sequence can be fed in. So, for example, you've got a sentence and each of the different tokens represents one of the inputs. Starting off with he, you would send this through the network. You would get like a hidden state, which would then be fed into the next input along with the next token. And you would do this through the network with each of the words being fed in. And they basically are able to take into account words that have previously been seen in the sequence. And then finally, you would get some sort of output which would be able to, do something like classify or translate or whatever like that. One of the problems, though, that I found that I read about with recurrent neural nets, though, is they have this problem called the vanish. They tend to forget what has come at the very beginning of a sequence when they get to the end of a sequence for long sequences, and this is called the problem of the vanishing gradient. Now, I don't understand the math behind this. I've written down that the problem is the derivative of the error being multiplied multiple times over many layers and basically disappearing. Don't ask me to explain what that means. But basically, yeah, like I said, it kind of forgets what's happened at the start of a sequence. So
I just wanted to contribute I know we don't have a lot of time, but just a tiny bit of like human intuition here. Like, I mean, just in general in our lives, if we're trying to work out causality, like it's much more easy for us to work out cause and effect over shorter time spans than longer time spans. And like, if you think of a sequence of things that then finished with a conclusion, like I'm able to work out what the impact of recent events was, but further events are harder. And I think that's like a conceptual equivalence of the math there.
Cool. Thanks, Alexi. That's great. Yeah. So basically, enter in the long short-term memory unit and the gated recurrent unit. And these are basically, very briefly, are able to hold on to pieces of information. So these units, so there's one here, the long short-term memory unit and the gated recurrent unit. These could be the same as what's in these different units just here. And without going into too much detail with how the information actually flows through, both of these are able to hold on to pieces of information and can decide what is important. And essentially can remember information from further back in a sequence than a vanilla recurrent neural net can do. And then, of course, you can basically do one of these things that goes in both directions at the same time. An example of that is a bidirectional recurrent neural network, which can get information in both directions of a sequence. So this is basically the same as what I showed here, but there's one going in this direction, and then with the bidirectional recurrent neural network, you've got one going in the opposite direction too. So just say you wanted the output at Y2, and you've got your sequence of words down here. One side would it would enter in on this side of the network. The hidden state would come out and go through the sequence here up to Y2. And conversely, the tokens at the other end of the sequence would be added in at the end and go through this other network and feed its way through to Y2 as well. So basically, if you had two sentences like this, he said Teddy Roosevelt was a great president, and he said teddy bears are on sale, you would know this first sentence would know that the word teddy is talking about a person because of what's actually come later on in the sequence, and it would know that in the second sentence, teddy is referring to a toy based on what's come further in the sequence as well.
And I will add here really quickly that this knowledge can be taken advantage of because these bidirectional RNNs or LSTMs or GRUs are often stacked. So the output from this one layer will then itself feed into another RNN where, you can get the forward and backward information in one node or one vector.
Thanks, Matt. All right, so the next thing is the sequence-to-sequence model. And basically what you've got here is you've got an encoder network and a decoder network. And the way that these work is that, again, this part in purple is a series of like either recurrent neural nets or long short-term memory or GRUs. And you might be feeding in like a sequence of words. You're not worried about the output. You're not worried about the hidden output here because nothing's coming out until the very end when it's processed the entire sequence, and the encoder sends all of the information to the decoder to do something. In this case, it's a question answering system. We've got how is the weather today, and it's decoding as it is sunny today. This kind of many-to-many model where you've got lots of inputs and lots of outputs is really good for machine translation as well, where you're doing from English to French or whatever. But then what they found with the basic sequence-to-sequence model is that this orange part is the encoder. There was like an information bottleneck at the final stage before the information was sent to the decoder. And there's a thing called attention for basically having some kind of weights. It attaches some kind of weights to each parts of a sequence so that the model actually like focuses on it. It's kind of like when you're reading a sentence, you're not going to focus on every single word in the same way. There'll be certain words in it which are more important than others, and this is basically addressing that. On the right-hand side here, you've got there's a heat map. I mean, I don't know if you can actually see the words, but you've got a series of words in French and a series of words in English, and this is basically showing how French is being translated into English. And the heat map shows the attention being put on a particular word at a particular time. And the lighter colored cells is where the attention is being focused. And you can see that there's like a sort of a quite a strong correlation between down this line and the sequence of words that are being converted from French into English is like, it's almost like the order in French is almost the same as the order in English is what I'm trying to say. And you can see most of this is black, which basically goes to show that the model doesn't really need to look at most of a sequence at any given point in time. It can just focus on certain parts of it. So this attention thing is quite important. from that, we're going into transformer. This was proposed in the paper, Attention is All You Need. I have a link to this actually at the end of the presentation. What this is basically a stack of encoders and decoders, kind of like there's basically a stack of both of these. And in each encoder, you've got its own neural network plus something called self-attention. And in the decoder, it's basically got the same thing. And the self-attention is subtly different to attention, and I might get this a little bit wrong, but if what I understand, self-attention is basically the way that it can associate words inside of a sequence. So, for example, if you had a sentence like "the animal didn't cross the street because it was too tired," the pronoun "it" could either be referring to animal or street. Self-attention is basically a system that would be able to determine which of those words it's pointing towards. And then finally, BERT, the bidirectional encoder representations from transformers. I couldn't find a good picture for this. This is where my knowledge gets really spotty. I apologize. Basically, what I can say about this is that it's a bidirectional version of transformer. When it's learning, being bidirectional, it basically would be able to see each other. Like the words when they're training would be able to see each other. I don't really know how to explain that. What it does though, it uses random mask tokens, which is something I mentioned a little while ago, to put in and also a bit of randomization. And it randomly puts these masks in the training data, and it forces the model to like learn those words that it potentially could have seen. So there's no sort of leakage there. And as I mentioned at the very beginning of the presentation, these BERT models can be pre-trained with large amounts of unlabeled text, which makes it really ideal for transfer learning, maybe after some fine-tuning, maybe not, depending on what you want to do. And I just wanted to add that Mr. Know Nothing, he concluded his notebook with a whole bunch of code that you could basically just like boilerplate code almost, that you could try running one of these models with. So it'd be a really good idea if you're interested to go and check that out. Just really quickly, I wanted to just have a quick look at the leaderboard. There's a few things I noticed with this, is that the score was quite good. I think they did quite well with their predictions. I noticed that the top 4 didn't move at all in the leaderboard from the public to the private, which I think was pretty interesting. But they did have a lot of entries. Some of the winning techniques. So many of them incorporated larger pre-trained models. As I mentioned earlier, you were able to use whichever model you wanted. And a lot of them use this thing called XLM Roberta, which is a terrifyingly huge model that was made by, I think it was Amazon? I forget. Which was trained with 2.5 terabytes of data. So a lot of people use that and just like fine-tuned this huge model. A lot of people did lots of ensembling, which seems to be a pretty common Kaggle strategy. There was some downsampling for a more balanced data set. So because the balance between toxic and non-toxic was so large, that would like make the non-toxic set smaller by randomly like removing a bunch of them. So basically the two classes were the same. There was some post-processing done. Some of the people would factor their output based on language. So for example, they would multiply or divide by a particular number depending on what language the test data was in. Some people fine-tuned the BERT model with specific monolingual models as well. And there was also a bunch of people who tried to translate the test data into English first using Google Translate, but apparently that didn't work so well. And I just like to add, I've added a bunch of different resources that I found really useful. Maybe you will as well. I've got some of the Kaggle kernels here. This first notebook is the one that I used to learn all about BERT. And this first video was I think was the best description I've ever seen of how a neural network works, from a group called 3 Blue 1 Brown. Really great videos. I recommend those. And I know we're running pretty short on time, so that's it. Thank you very much for listening. Any questions?
Thank you so much, Mark. I would like to invite everyone to come together and actually give Mark a hand. I think this is actually one of Mark's first presentations. So if you could join me on 3. 1, 2, 3.
Thank you.